In a previous video, we talked about what happens if you have a magnetic field in a region and maybe a loop of wire with a resistor, and you move this, you pull this loop of wire out of that magnetic field. So here's my magnetic field, this loop, and I pull it out, and based on the forces acting on the charges, we could calculate a voltage and a current, which is measurable, and you can determine that. Okay, but additional experiments show that I can generate a current in this wire without moving the wire, but changing the magnetic field. And so we'll talk about that a little bit later, the changing magnetic field. But the connecting piece is basically saying, well, how much magnetic field is going through this loop? Okay, so here is a section of the loop in which there is magnetic field coming through it. And so our question for this video is just to understand what is that, so that we can then use it for some later analysis. And we call that the magnetic flux. Okay, and by its name, it makes sense. Flux is kind of a how much is going through something. This is how much magnetic field is going through this loop. Okay, and basically it depends on, well, how big is the magnetic field. If you have a big magnetic field, then you have a lot of magnetic field lines. And also, well, how much area of the loop has magnetic field going through it. Okay, so for a simple case, if I have this square loop and it's entirely inside a magnetic field that's perpendicular, okay, so this B field might be out of the page at you. Well, that means it's filling the entire loop, and if I draw a side view, it's piercing it perfectly, okay, everywhere. So that means the flux, the magnetic flux, is equal to BA. Now we give that a symbol. Okay, we give it this symbol. All right, that's an uppercase theta. All right, and so we use it for flux. Okay, so in this case, the field was perfectly perpendicular to the loop, and it filled the entire loop, and it was constant. So it's the size of the field times the total area of the loop. Now in this case, it's not filling the total loop, so it's some fraction of it. It's going to be just this much. All right, so we have to kind of build it a little bit better. But let's add one more situation. What if my loop is kind of tilted, but my magnetic field is still going this way? Okay. Well, now not as much field's going actually through it. We need to know how much is going perpendicularly through it. So how much of those vectors are actually going straight through the loop? Okay. Well, if we remember that for a loop, I'll draw the loop again. This is a side view of a loop. We'll just assume current's flowing such that its dipole moment is that way. Okay. And if the B field makes some angle with that, now, when we considered torque, we cared about how perpendicular those were. But here we want to know how much is going straight through, which means we want to know the component of B that's parallel to mu. This would be B parallel. And we want that one. We want to know how much is going through it. So if we used a cross product to find how much was perpendicular, then we want to use a dot product to figure this out. So we can adjust this to say, okay, in this case, our flux is going to be equal to B dot A, but A is going to have to be a vector now. And so we choose A, the direction of A, to be in the same direction as mu. All right? Okay, so that helps us. That helps us a bit. Now let's go to the case where, well, B is not necessarily constant. Well, all that means is we have to integrate. Okay? So our full form would mean, okay, it's not constant, so it's going to be constant over small enough areas. So if I choose little dA's, small enough that B is effectively constant over the small areas, then I just have to integrate over the loop where that's true. Now, we won't do any cases where it's really weird, like a continuously changing function. But we might do what's called piecewise constant. This would be an example of a piecewise constant. For part of the loop, it's one value, and for the other part of the loop, it's a different value. In this case, 0 here and some value B here. Okay, we could do something like, here's a loop and we have 1/3 of it is 3, 1/3 is -2, and 1/3 of it's 0. Okay, we can integrate over the whole loop by just breaking it into 3 different pieces and find out what the net flux is. Now the negative implies there is a sign to this. So if A is in the direction of mu and B is going the other direction, then we're going to get a negative sign. And so we've got to make sure we take that into account. So we get a total amount of flux in one direction. So that's magnetic flux. Again, symbol is this, and its full-blown nature is this, but basically it boils down to magnetic field times area. We just have to be careful in case there's an angle associated with it, and if it's not constant.